I made a video on computing the Fibonacci sequence, and one of the viewers tried out, I wrote some Python code and he implemented it and he checked it against Wolfram Alpha, and he asked my algorithm to compute the 1000th Fibonacci number, and Wolfram Alpha asked it what's the 1000th Fibonacci number, and there was a disagreement in the last few digits. They disagreed. So Wolfram Alpha is very credible. So what's the problem with my algorithm? And it's not that the formula is wrong, it's that the computer can only store a finite amount of information when it stores double precision floating point numbers, and there's error that accumulates in the formula, and I want to show how that works. Okay, let's review what the Fibonacci numbers are. The f sub 0 is 0, f sub 1 is 1, and here's the recursive definition. The way you get the next Fibonacci number is just the sum of the two previous ones. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. And that's how we get the Fibonacci numbers. So the question is there a formula for the nth Fibonacci numbers without computing the numbers before it? Like if I want the 1 millionth Fibonacci number, do I have to add up all the numbers before it, or is there a way to just explicitly calculate the 1 millionth Fibonacci number? And the answer is yes, there is a formula. It comes from the theory of generating functions, where you define a power series where the coefficient of the power series are the terms from the series, and that gives you a function, and you solve for that function, and then you use Taylor's theorem to come up with an alternative definition for the coefficients of the power series, and you end up with this: the golden ratio to the nth power divided by the square root of 5. And so this was the algorithm I gave, and then this person tried out this algorithm and saw that it gave the wrong answer in some cases. So let's look at that. Okay, this person's name is BoomZATVZ, and he made a video response to my algorithm. So he asked my algorithm to compute the 1000th Fibonacci term, and he got this. And then he asked Wolfram Alpha to compute the 1000th Fibonacci term, and he got this. And he's zooming in at the last digit. So let's watch him do that. That's what my algorithm says, and he's pointing out the last few digits end in 6528. That's what my algorithm says. Now he's going to go over here to Wolfram Alpha, ask it for the 1000th Fibonacci number, and it ends in 8875. So Wolfram Alpha is very reputable. They're probably correct. So what's wrong with my algorithm? So if you look at my algorithm, you have to raise the golden ratio to the nth power. The golden ratio is 1 plus the square root of 5 over 2. So the computer can only store about 16 decimal digits when it uses double precision floating point arithmetic, which is primarily what's used on computers. We may think of computers as infinitely accurate and always getting the right answer, but as soon as you have to numerically take the square root on a computer of a number that's not a perfect square, the computer cannot hold all of the digits. I mean, if it's doing it symbolically, if it knows it's the square root of 5, like if you're using Mathematica and it symbolically understands square roots, it can do manipulations. But as soon as you convert it to a floating point number, you lose all that, and you only get 16 decimal digits. So the way we know we get 16 decimal digits is because a double precision floating point number has 53 bits in the mantissa, and 1 over 2 to the 53rd is about 10 to the minus 16. So this is a really small number, like 0.000001, 15 zeros, then a 1, a tiny, tiny number. So we can't, so when we take the golden ratio to the nth power, we're not getting exactly that. There's some error in there, what I'm calling epsilon, some small number. So we're going to use the binomial theorem. So here's the leading order term. This is the exact term, but then we get this error term, epsilon, machine error, times this other stuff, plus order. This should be epsilon squared. So if epsilon is a small number, epsilon squared is a really small number. So since we're rounding this, we're saying when is the error approximately 1? Because if the error is approximately 1, then when we round it, we're going to get the wrong answer. So we want to solve for n, which Fibonacci number is going to be the first one to give us the wrong answer in this formula. Now this is a little tricky to solve for because we have n multiplying by and then we have n in the exponent. So let's just tabulate this using Python. So if we go over here to Python, define epsilon to be 1 over 2 to the 53rd, which is about 10 to the minus 16. Define phi to be the golden ratio, and let's just print this out. Yep, that's what we got. Now let's just do this loop. Rather than inverting this function, let's just tabulate it. We'll start off at n as 1. Here's our formula for the error. This is the error in the expression I gave for the nth Fibonacci number. So for the first few Fibonacci numbers, we see these really, really small errors, but they're getting bigger. They're getting exponentially bigger, 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 bigger. And here at around 68 or 69, the error exceeds 1. So we would expect my formula to give the wrong answer around here because the error for the nth Fibonacci number is about 1 or 2. There's a more sophisticated way of solving this equation. This is difficult to invert because we have n as a multiplicative factor and n as an exponent. If it was just in an exponent, we could take a logarithm. So this kind of thing, you need to use this Lambert's W function, where Lambert's W function is the inverse of this function, x times e to the x. So anytime you have multiplication and exponentiation, a lot of times this Lambert's W function will work. So if we want to solve this equation, we can just go through this manipulation, and it says when n is about 68 and a half, that's when this error equals 1, which agrees with what when we tabulated it, we saw the same thing. And so yeah, from scipy.special functions, import Lambert's W function. We just plug this thing in here and we get, 68 and a half, which is consistent with what we saw here. Yeah, in between 68 and 70, the error is 1. So around here, our Fibonacci formula is going to fail using double precision floating point numbers. So the original algorithm, I was talking about computational complexity, and this one is exponentially hard because you're making all these extra recursive calls. This one is faster, but this is still linear time because you're only asking for the nth Fibonacci number, but it's computing all n of them. Whereas this one here is computing only the nth one, but the difficulty is here. All this whole video, all this rigmarole, this whole video is concerned with the error in this term here, phi to the n, to the nth power. That's difficult to do with double precision floating point arithmetic, and it turns out you only get the correct answer for about the first 70 Fibonacci terms. But the advantage of this one is that it's easily parallelizable. Suppose you were on a GPU or something like that, where you can evaluate all these terms in parallel. There's no recursive dependence on earlier terms. So this has a lot of parallel advantages, but it's very difficult. It's very fussy with the floating point arithmetic because of this term here. So now let's compare these terms. This one, the other thing is Python has arbitrary precision integer arithmetic. So as your integers keep getting bigger and bigger and bigger, it will store them as lists of bigger and bigger numbers. But the same is not true for floating point numbers. So we're comparing the integer version versus this floating point version. So to begin with, here's just the ith Fibonacci number. To begin with, they agree. And this column here is their difference here. So to begin with, they agree. Difference is 0, difference is 0. Then we get way down here. So here's the first one that's different. The 71st Fibonacci number using Fib2. So this one is correct because Python's using arbitrary precision integer arithmetic. But this one is not correct because the floating point arithmetic is finite precision. So we predicted at around 68, it would be wrong, but here, actually at 71 is the first time they're different, and then they're different after that. And here's just an example. I said, well, what's some large number times some large number? And these are integers, so it returns some gigantic integer. But now if I put a decimal point at the end, that's the same two numbers, but with a decimal point, now we no longer get, in fact, it gets the wrong answer. We get a little 1 right here, which obviously that's not right. So we have finite precision floating point numbers that the computer's using. So you might ask the question, how small does epsilon need to be in order to get the nth Fibonacci number correct? So from our Taylor series, we knew this is the error term. So we want the error to be less than 1 so that when we round it, we get the right answer. So if you just solve for epsilon, so your epsilon has to be exponentially small. If we want, say, the 100th Fibonacci number to be correct using this formula, we need a really, really small epsilon. And that means you can't do it with double precision floating point numbers. You're going to have to use some kind of extended precision or use Mathematica and ask for lots and lots of digits. Otherwise, you're going to get it wrong. And so that explains the problem here is that what we want is an exact formula for the golden ratio to the nth power, but because we can only store a finite number of digits, we have this little error thing is polluting our exponential, and so this is the exact correct answer and this is the error. So this error term is messing everything up, and that's what was messing up in that demo when that's the reason why this numerical thing was getting the wrong digits. He was asking for the 1000th Fibonacci number here, so it was only correct up to the first 70 Fibonacci numbers. After that, you need more accuracy. And I hope you learned something. If you didn't learn anything, then you are really smart.